The hidden oceans that could change everything we know about life. Picture this. Right now, while you're reading this, there are oceans beneath miles of ice on distant moons that might be teeming with life. I'm not pitching you a sci-fi movie here. This is real. NASA scientists have solid evidence that Europa and Enceladus, two seemingly frozen moons orbiting Jupiter and Saturn, are hiding massive liquid oceans under their icy shells. And you know what they say, where there's water, there's hope for life. These aren't just dead, frozen rocks drifting through space. They're dynamic worlds with geysers that shoot water hundreds of miles into space, cracked surfaces that hint at something moving underneath, and enough energy to potentially keep organisms alive. We're past asking if these oceans exist. The real question now is, what's swimming around in them? Let me walk you through why scientists are so convinced these hidden oceans are real, and why they might actually be the best shot we have at finding alien life in our cosmic neighborhood. How we discovered these hidden oceans. The story begins with Voyager. Back in the late 70s and early 80s, the Voyager spacecraft zipped past Jupiter and Saturn, beaming back humanity's first close-up shots of their moons. When those images of Europa came through, scientists couldn't believe their eyes. Unlike our pockmarked moon, Europa looked bizarrely smooth, covered in cracks and ridges that stretched across the entire surface like a windshield after a bad hailstorm. Those cracks were telling us something important. They meant the ice wasn't just sitting there, frozen solid for eons. Something was moving it, breaking it up, constantly reshaping it. The only thing that made sense, a liquid ocean underneath, creating pressure and movement that cracked the ice from below. Then the magnetic field data came in. When Galileo orbited Jupiter through the 90s and early 2000s, it measured Europa's magnetic field and found something wild. The moon was generating its own induced magnetic field. This happens when a conductor moves through Jupiter's powerful magnetic field. And what's the best conductor out there? Salty liquid water. That's when everything clicked. Europa wasn't just a giant ice cube. It was an ice shell floating on top of a global ocean, possibly holding twice as much water as all of Earth's oceans combined. Enceladus announced itself even more dramatically. In 2005, Cassini spotted something nobody saw coming. Enormous plumes of water vapor erupting from cracks near the moon's south pole. We're not talking about small puffs here. These were massive geysers shooting hundreds of miles into space, powerful enough that Cassini could actually fly through them and analyze what was inside. The plumes had water, ice crystals, salt, and organic molecules. Exactly the kind of chemistry you'd expect from a liquid ocean touching a rocky core. Enceladus was literally spraying samples of its ocean into space for us to study. Here's what blows my mind about this. Finding liquid water in the outer solar system, where it gets down to about -300 degrees Fahrenheit, shouldn't even be possible. Water should be frozen harder than concrete. But these moons have a secret heat source called tidal heating. Think of it like this. As Europa orbits Jupiter and Enceladus circles Saturn, the massive gravity of these giant planets constantly squeezes and stretches them. That endless flexing creates friction deep inside, and friction makes heat. Enough heat to melt ice and keep liquid water flowing for potentially billions of years. The evidence just kept piling up. Scientists studied how Europa's surface features line up with its orbit and realized the ice shell is probably floating on liquid, spinning at a slightly different speed than the rocky core beneath. They measured how Enceladus wobbles in its orbit and found it wobbles way too much to be solid all the way through. There has to be liquid in there acting like a lubricant between the surface and the core. More recently, Hubble spotted what look like water vapor plumes shooting up from Europa too, just like on Enceladus. If that's confirmed, it means we could potentially sample Europa's ocean without having to drill through miles of ice. The scale of all this is mind-boggling. Europa's ocean might be 40 to 100 miles deep. To put that in perspective, Earth's deepest ocean trench, the Mariana, is only about 7 miles deep. Enceladus is smaller, but it still has a global ocean hiding beneath 6 to 12 miles of ice. This isn't theoretical anymore. We've got magnetic fields, surface features, and direct observations of plumes, all pointing to the same conclusion. There are enormous liquid oceans hiding beneath the ice on these distant moons. Europa, Jupiter's mysterious icy moon. Let's take a closer look at Europa, because this moon is genuinely unlike anything else we've ever seen. Europa is roughly the size of our moon, but that's where any similarities end. Its surface is one of the smoothest in the solar system, with hardly any impact craters. That tells us the surface is young, geologically speaking, of course. Something is constantly resurfacing it, erasing the evidence of asteroid impacts over time. That something is the ocean below, pushing up through the ice and creating new terrain. The surface is this incredible puzzle of what scientists call chaos terrain, ridges and lineae. Those long cracks I mentioned. Some of these cracks stretch for thousands of miles. Scientists think they form when the ice shell flexes and fractures as Europa swings around Jupiter. The cracks often look reddish-brown, probably from salts and other stuff that's bubbled up from the ocean and gotten zapped by Jupiter's brutal radiation. Here's where things get really interesting. The ice shell is probably 10 to 15 miles thick on average, maybe thinner in some spots. Below that sits an ocean that could be 40 to 100 miles deep. When you do the math, you realize Europa's ocean has more water than all of Earth's oceans put together. We're talking about a truly massive body of liquid water that's been stable for potentially billions of years. But the ocean isn't just sitting there cold and dark. Tidal heating from Jupiter keeps it liquid and creates temperature differences throughout. The ocean floor is likely in direct contact with a rocky mantle, and that interaction between water and rock could create hydrothermal vents, just like the ones at the bottom of Earth's oceans. Those hydrothermal vents on Earth? They're entire ecosystems. They support life in total darkness, using chemical energy instead of sunlight. Weird organisms cluster around them, feeding on chemicals gushing out from inside the planet. If Europa has similar vents, it could have similar life. The chemistry looks promising too. Those plumes Hubble saw, plus the materials on the surface, suggest the ocean is salty and full of organic compounds. Not life itself, but the raw materials. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, all the elements life needs to get started. Europa also has something else crucial: time. The ocean has probably been there for most of the solar system's 4.5 billion year history. Life on Earth took a few 100 million years to show up. Europa's ocean has had over 4 billion years to work with. That's a lot of time for chemistry to try different things. Now, the radiation on Europa's surface is absolutely savage thanks to Jupiter's magnetosphere. Standing unprotected on the surface would kill you within a day. But here's the good news: that radiation doesn't go deep into the ice. A few feet down, you're shielded. In the ocean itself, you're completely safe. The radiation might even help by breaking apart water molecules at the surface and creating oxygen, which could then get mixed down into the ocean. NASA's Europa Clipper mission is launching in 2024 and will fly by Europa dozens of times, mapping the surface, measuring how thick the ice is, and analysing those plumes if they're still active. It won't land, but it'll give us the most detailed look at Europa we've ever had. The mission will tackle some crucial questions. How thick is the ice really? How active is the ocean? What's the chemistry like down there? And ultimately, could anything actually live there? Enceladus, Saturn's tiny ocean world. Now let's talk about Enceladus, because this tiny moon might actually be the most exciting place in the entire solar system to hunt for life. Enceladus is small, really small, only about 300 miles across, roughly the width of Arizona. You could drop it in Texas and have room left over. But what it lacks in size, it absolutely makes up for in drama. The South Pole of Enceladus is one of the most geologically active places we've found anywhere beyond Earth. Those plumes I mentioned, they're shooting out of 4 massive cracks scientists have nicknamed tiger stripes. These fractures run parallel to each other, each about 80 miles long and a mile wide, literally glowing with heat against the frozen backdrop. The plumes blast water vapor, ice particles, and organic molecules hundreds of miles into space at speeds up to 800 miles per hour. Some of this material escapes Enceladus completely and forms Saturn's E-ring, a faint ring made almost entirely of ice particles from this one tiny moon. Enceladus is literally feeding one of Saturn's rings with its ocean water. Cassini didn't just watch these plumes from far away, it flew right through them, multiple times. The spacecraft directly sampled what was inside and found something incredible: molecular hydrogen. This is huge. Molecular hydrogen gets produced when hot water reacts with rock in a process called serpentinization. It's the same thing that happens at hydrothermal vents on Earth's seafloor. Finding hydrogen means Enceladus has active chemistry happening right now where its ocean meets the rocky core. And here's the kicker: hydrogen is food. On Earth, microorganisms called methanogens eat hydrogen and carbon dioxide to make methane and energy. They thrive in pitch-black environments with no sunlight, living purely off chemical energy. The plumes from Enceladus have hydrogen, carbon dioxide, and methane. That's exactly the chemical fingerprint you'd expect if similar organisms were living there. I want to be clear, we're not saying there is life on Enceladus, we're saying the chemistry is right. The energy is there, the liquid water is there, the organic molecules are there. Every ingredient life needs is present and mixing together in an active ocean as we speak. The ocean itself is global, sitting under an ice shell that's about 6 to 12 miles thick at the South Pole, possibly thicker elsewhere. The ocean is probably 6 to 10 miles deep, touching a porous rocky core. Tidal heating from Saturn keeps the South Pole warm enough that the ice stays thin and fractured, letting the ocean break through. What makes Enceladus even better than Europa for study? Those plumes. We don't need to land on it. We don't need to drill through miles of ice. We can just fly through the plumes, grab samples, and analyze the ocean chemistry directly. Enceladus is basically handing us ocean samples on a silver platter. The salt measurements suggest the ocean is similar to Earth's oceans in concentration. The pH is probably alkaline, somewhere between 9 and 12, which matches conditions at Earth's hydrothermal vents. The temperature at the ocean floor could hit around 200 degrees Fahrenheit near active vents, warm enough to drive some seriously complex chemistry. Scientists have even found complex organic molecules in the plumes, including compounds with hundreds of atoms. These aren't simple stuff. They're the kind of building blocks that could potentially assemble into more complicated structures given enough time and the right conditions. Time matters here too. Enceladus's ocean has probably been active for at least hundreds of millions of years, maybe much longer. That's plenty of time for chemistry to get creative. Life on Earth showed up relatively quickly once conditions were right. If the same could happen on Enceladus, it might have already. The energy available on Enceladus is impressive too. The tidal heating puts out about 16 gigawatts of power, roughly the same as 20 large power plants running non-stop. That energy drives the plumes, heats the ocean, and powers all the chemistry happening at the seafloor. Future missions are already in the works. NASA's proposed Enceladus Orbilander would orbit the moon, fly through the plumes over and over, and eventually land near the Tiger Stripes to study the ice and maybe even drill down to touch the ocean directly. The mission could look for biosignatures, chemical traces that life leaves behind. The case for life on Enceladus isn't wild speculation. It's built on direct measurements of an active ocean that's mixing water, rock, and organic chemistry right this second. If life can emerge from chemistry alone, Enceladus is showing us it has everything necessary. Other candidates hiding oceans. Europa and Enceladus grab most of the headlines, but they're not alone. The outer solar system might be absolutely packed with hidden oceans. Ganymede, Jupiter's largest moon, and the biggest moon in the whole solar system, probably has a subsurface ocean too. Magnetic measurements from Galileo and later observations from Hubble point to a salty ocean buried under about 100 miles of ice. The ocean could be 60 miles deep, sandwiched between different layers of ice in this complex structure, totally unlike what we see on Europa or Enceladus. Callisto, another big Jovian moon, shows similar magnetic hints of a subsurface ocean, though it's probably buried even deeper, under 150 miles of ice. The surface is ancient and beat up with craters, showing barely any geological activity, which means getting to that ocean would be incredibly hard. Titan, Saturn's largest moon, is its own weird category. It's got lakes and rivers of liquid methane and ethane on its surface, but underneath, buried beneath a crust of water ice, there's probably a liquid water ocean mixed with ammonia. Cassini detected gravitational oddities consistent with a subsurface ocean about 30 to 60 miles down. Even Mimas, a tiny Saturn moon, recently shocked scientists with hints of a possible ocean. Mimas looks completely dead from outside, heavily cratered with zero signs of geological activity. But orbital measurements suggest something liquid might be sloshing around inside, hidden under a thick ice shell. The pattern is clear. Icy moons with enough tidal heating can keep liquid water oceans going for billions of years. The outer solar system isn't the frozen graveyard we used to think it was. It's full of hidden oceans, and every single one could potentially host life. Why these oceans could actually harbour life. Okay, so we've established these oceans are real. Now let's talk about why they could genuinely support life. Life needs three things: liquid water, energy, and the right chemistry. These moons check all three boxes. The water part is obvious. Vast liquid oceans that have been stable for billions of years. That's actually more time than life needed to get started on Earth. The energy comes from tidal heating and chemical reactions. On Earth, the first life probably didn't use sunlight at all. It used chemical energy from hydrothermal vents. The same kind of vents we think exist on Europa and Enceladus. Organisms on Earth absolutely thrive in these environments, living off hydrogen, methane, and sulfur compounds. The exact same chemicals we've detected shooting out of Enceladus. The chemistry works too. Organic molecules, salts, the right pH levels, everything mixing together in warm water near a rocky seafloor. Here's what gets scientists genuinely excited. These oceans might actually be better for life than Earth's surface ever was. They're shielded from cosmic radiation by miles of ice. They're stable, isolated from all the chaos that happens on planetary surfaces. They have energy sources that don't depend on sunlight at all. If life got its start in Earth's oceans first, maybe that's actually the standard template. Maybe ocean worlds are where life typically begins. What comes next? We won't know for sure until we go there and look. Europa Clipper launches soon, and proposals for Enceladus missions are already on NASA's desk. Within the next few decades, we might actually have real answers about whether we're alone out here. The evidence we already have is pretty compelling. Hidden oceans exist. That's not in question anymore. They're geologically active. They've got the chemistry and energy that life needs. We're past asking whether these oceans could support life. The question now is whether life actually took the chance when it had it. The universe might be far less lonely than we thought, and the answers might be waiting for us right now, swimming in dark oceans beneath alien ice.